So thanks to friends of Copley, Trio. This is a Trio EtherCAT master. Got an EtherCAT in, EtherCAT out, and you can hook up the power down here. That works good with the Copley XEC and BEL. These AC power drive, DC power drive. The Trio motors are 200 volt windings. So to go 6,000 RPM, you'd need the 200 volts or 120. If you use 48 volts, you'll probably be around 1,500 RPM. So Zenus Compact is ideally suited. This is one of the smaller, like a NEMA size 23. It's a Japanese size actually, but this has the 23-bit encoder. That's like the Nikon A format, and this is a 750 watt motor. I've got it running off of the Zenus Compact, and it has the T option, which is the 17-bit, or it's like a Tamagawa, a little bit of a Tamagawa knockoff, but it conforms to the Tamagawa spec. When you connect the feedback connector, just be sure to look for the key and get it aligned properly to tighten down. You don't want to misalign that. It's plastic, so just be careful when connecting this. There's a battery in here with a loop back that goes to the motor to store the multi-turn position. If you plug this in or unplug it from the battery, you will get a fault. I got a fault indicating an encoder fault, which is just the battery's disconnected and was reconnected. So you'll lose multi-turn. This is not a battery free. So let's take a look at the wiring of the feedback device. So we have the cable on the motor, and we can see there's a pinout here. So pin 7 and 8 are the slave or data. Pins 5 and 6 are the master clock or bidirectional communication on the data lines, but this would be like a master line. And then there's a battery on 9 and 10, and that's where the loop back comes in. You'll see that these two pins here at the top with the little pointy edges here, the battery comes on the red and the black, and then goes down with the white and the brown. So I had some challenges with this cable. I had a previous cable with a different color code, but that's okay. Just go by the pinout, and then when we connect to the Copley, we just need the data lines, and no master lines. So it's pure bidirectional, so there's no clock. This is the Tamagawa type Absolute A feedback device. Yeah, see, the previous one had a black, orange, blue with yellow going back to the battery, and this one has the gray, green, black, and white going back to the black going back to the battery and the white going to the motor. Anyways, pretty easy to cable up, and we'll take a look at the basic setup with CME. So initiating CME, we changed it's a brushless rotary motor. This one has no brake. It's a Tamagawa, so we just picked the Tamagawa Absolute A and not the Nikon A, so this is the 17-bit one. 17 bits of single turn, 16 bits of multi-turn, 2.5 megabit. There will be a battery fault you could ignore the battery fault, but if it's like just a velocity application or you only care about single turn, but if you want the multi-turn, do not ignore the battery fault. In this one, on power up, I get a CRC fault, and I think that's just to do with a slight discrepancy in the spec between the Tamagawa and the manufacturer of this feedback device. So I'm going to allow 3 consecutive CRC faults on power up or reset because I find CRC faults to be very annoying. But for the moment, I'm just going to set it to 0, and we'll see what I'm talking about. And set up for the EtherCAT and emulate it out if you ever need feedback out. So on the control panel, we can see that we had an encoder fault. And if we click on the error log, you can see you have an encoder fault, but you want to see the details. Here are the details. There's a multi-turn error, a battery error, and an error bit indicating that you better check your homing because it's not going to be what it used to be. So with this feedback device, I'm very close to the original single turn position. And what I'm going to do is just, I can turn the shaft a little bit. You could do multiple turns, but you could dial it back to the 0 position. If you're going to do some homing, you move the motor to the 0 position, move your stage or whatever to the 0 position, and then connect the motor. That's like, the dumb way for absolute positioning, but it sure is easy. Sometimes your motor will have multiple turns though, and you'll have to get it back to 0. So yeah, maybe I get multiple turns at some random position. I could have a big multi-turn number there. I'm going to clear the fault, and you can see in the error log that the fault goes away and the encoder status is clear. So now that the battery's connected, we can do some homing. I'm just going to make an absolute move to the 0 position. So I'm just going to rewind the motor. So now I'm in the 0 position. I move my mechanical system to the 0 position and I connect it, and everything will be good. Or you say, no, I don't want to do that. I want to do some homing. And I'm going to say, let me disable it. Motor comes in some random position. Maybe it's more than a single turn. And I'd like to do homing with that. Well, if there's no homing executed, this is the position from the motor, uncorrupted by the homing routine. So normally I would do set current position as home, save it, exit, and if your homing method was something else, then you have to uncalibrate it first before you can calibrate it. So if it was set at absolute immediate active home, then you have to set it to set current position, save it, exit. And now when I reset the drive, of course, it's going to come back to the same position. That's just the position read from the encoder because the homing routine was not executed. And no CRC fault this time. That's good. Oh, wait a minute. There it is. So on power up or reset, you get a CRC fault. It's very annoying. It's just a timing issue. And I'm going to get the protocol and see if we can update the firmware to fix that. But my little short-term fix is just allow 3 consecutive CRC faults in a row, and then it should power up okay. So let's do that again, reset the drive, and I move the motor to the position I want to be 0, and I've connected the motor to my mechanical system. So I want this position, whatever it's at, to be 0. So I have to put in minus 257055. And then I can execute the homing, and then don't forget to save it before you exit. So now every time I power cycle, it used to be 2 revs from 0. now it's that's the 0 position. And again, in order to calibrate something, you first have to uncalibrate it. Okay, so save and exit. You can see the homing routine's been executed. That's the 0 position. And now when I reset it, it's not going to come back to 0 because it's just reading the value from the encoder. See, no homing has been executed. There's that position again. And now I can calibrate it. Okay, oh well, that's the same value, so I'll just save it and exit. And then this time when I reset the drive, it'll come back to that position. Okay, so that's a lot of fun with the Absolute encoder. So we can find the data for the motor. Trio specifies the part number, volts and amps, and T and L for 17 or 23 bit. So that's important. And I had to hunt down the S-tune data, but it's a 08A motor, so 750 watts. Newton meters, 2.39. Peak, there's a different winding here, so you got to be careful on the rating. Amps RMS, not Copley's amps peak. You get a rated speed, a theoretical top speed, and I measured the resistance and inductance. So let's take a look. Here's your torque constant. Here's your continuous and peak torque. There's the inertia. It's a 10-pole motor, so that's good to know. They're all 10 poles here. And I measured 2 ohms, and I multiplied that by 3 for millihenries, and that seems to work for most of these motors. So you don't need to ask what is the inductance. Just multiply the resistance by 3, and you get a roughly value. You're going to tune the current loop anyways. The Newton meters per amp, like once you know the torque constant, you get the back EMF constant in volts per radians per second for free, and it's 50 volts per kRPM, so about 3,000 RPM minus some IR drop. If I hit calculate, I take the torque and divide by the torque constant, and I get the current, and we should confirm that the current looks good, peak and continuous. Check the bandwidth. Make sure the velocity loop is out of the way for what you want to do, and did the tuning. Let's take a look at a move here, and we'll make a relative move at 1 rev 131.072. Bang. So profile velocity following your actual current in phase. I think I want to go a little bit further. Let's do a 10 rev. So it would be nice if I could take a look at the ripple here. So let's go a little bit longer trace time. So once we get to speed, we start seeing some, there's a little bit of ripple through there, ripple current. So we could do the cog comp on this. You can see the pattern repeating with every electrical cycle. But it's not bad. It tunes up really good. So while we're moving, it's plus or minus, I don't know, 3, 4, 5, 10 counts. Measurement tab, peak to valley. Oops, lost it there. So about plus or minus 30 counts. So not bad. That's pretty much it for the tuning. When I powered up last time, I did get a CRC fault, but when I reset it, it cleared the status. So CRC fault, don't ignore more than 3 just on the power up, and you'll be fine. If you do have CRC fault while you're running, then that's cabling, grounding, shielding. So make sure we get the shield connected to the frame ground, and otherwise good cabling. That's it. Thanks for watching.